Hello, I'm Swapnanil, and today I'm going to talk about calculus. Okay, I'll start from functions, and I'll gradually walk you through, the limits, derivatives, and so on. Okay, so let's talk about functions first. Okay, so what is a function? A function is like input and output. Okay, so you have an input, and this is a function f. X is the input variable. Okay, and you have an output. Okay, so for example, let's take a specific form of a function like f of x is x squared. All right, so when x, the input, is 2, then f of x is what? It's simply 2 squared, okay, which is 4. Right? So if you take a different function, for example, if you take f of x is 3x plus 2, let's say, okay? And let's say x is still 2, x is equal to 2, or let's take a different number, okay? Let's say x is equal to 7. All right? So what would be f of x? So f of 7, okay, you see, in the place of x, I write 7, is equal to 3 times 7 plus 2. Okay? So 3 times 7 is 21, 21 plus 2 is what? 23. Okay, so this thing is 23. Okay, so you see, depending on the functional form, okay, whether it's 3x plus 2 or x squared, your functional value is different, okay? I mean, even for the same input, okay? I changed the input here, okay? But if I took 2, for example, let's actually, just see this example. Let's compare these two functions, okay? So one is f of x equal to x squared, and the other is this function, okay? And let's say your input is 2, okay? So when x is 2, you get 4. If you plug in x equal to 2 here, what do you get? You get 3 times 2, and I simply replace x by 2, plus 2, which is 8. You see, your outputs are different, okay? Even for the same input, okay? Even when the input is 2, in both the cases. Your outputs are different because the functions are different, okay? All right, so function is simply an input-output kind of relationship, all right? And this tells you what the output would be for a given input. Okay. So this is really all you need to know about functions. Okay. Now there are different types of functions. Okay. So for most of the calculations in physics and in engineering, the functions are very smooth. Okay. We're kind of lucky in that sense. And by smooth function, what do you mean by that? Let me just show you the graphical representation of the function. Okay. So let's say you're trying to draw a function, okay, graphically. So this is your independent variable, and this is f of x is a dependent variable. And let's say your function kind of goes like that, okay? It's an arbitrary function, okay? I mean, as you can see, all right? But this function is smooth, okay? What that means is, it's not discontinuous, okay? Like, for example, you could have had a function which would have been something like this, and then it jumps, okay, and then it does something funny here, okay, and so on and so forth. None of those issues are there in this function, okay? It's smooth, and I will define why this function, okay, is different from that one, okay? I mean, when we discuss derivatives, you'll understand that this point is very different from that one, okay? We'll get to that later, okay? And as you can see, that this sort of jump, okay, is not present in a smooth function, okay? So that's kind of the intuitive way to appreciate a smooth function. Anyway, so let's, so for most of the purposes, okay, in the application of calculus, we deal with smooth functions, okay? At least at this level, okay? All right, so let's talk about limit, okay? So what is the limit? What is the limit of a function, okay? So limit means, let's say this is x equal to c, okay? And you are approaching towards c, okay? So the question is, so at this value of x, this is the functional value, right? But as you go closer and closer to x equal to c, your functional value changes, okay? So this y-axis is, tells you the functional value, okay? So when x is equal to c, when x is very close to c, the functional value is very close to, f of c. Okay, so you write this as limit x going to c, f of x okay, is f of c. Okay, and this is true for smooth functions. All right. So let's take a concrete example. So for example, let's say we're trying to find limit x goes to 3, x squared plus 9. Okay. How do you evaluate that? You simply plug in x equal to 3, okay, in this expression. So you get 3 squared plus 9, okay, which is what? Which is 9 plus 9 is 18, okay? So this is the meaning of limit, okay? So the question comes, why kind of do this fancy thing, like limit x goes towards 3? I mean, why not just evaluate this function at x equal to 3? And why do you need this concept, limit, okay? It will be clear in the next example. Okay, in this example, for smooth functions, it really doesn't matter whether you're approaching towards a certain point or you're finding the functional value at that point. Okay, they're the same. Okay, as you can see here, right? As you approach towards c, the functional value approaches towards f of c. Okay, the value of the function at that value of x. Okay, but the concept of limit becomes important, okay, when the functional value isn't quite defined. Okay, you can't quite see immediately what the value of the function is at that point. Okay, so do you have an example? Okay, let me give you an example of that type of a limit or of that type of a situation. Okay, all right. So for example, let's say you're trying to find the following limit. Okay, limit h goes to 0, okay, x plus h square minus x squared divided by h. Okay, h is, it's a variable, it goes to 0, and let's say in the numerator you have x plus h square minus x squared, in the denominator you have h. Okay, how would you find this limit? Okay, your first instinct probably would be to just plug in h equal to 0. Right? I mean, we can do that, okay? So let's do that. So let's write x plus 0 squared minus x squared divided by h, okay? I mean, h is also 0, right? So I should actually write 0 here, okay? So what do I get? You see, in the numerator, you have x squared minus x squared, which is 0, and in the denominator, you have 0, and, we are in trouble, right? Because you don't know what this is, right? It looks undefined, or, it's a... Okay, so the functional value, okay, is not defined. Okay, so what do we do? I mean, does it not have any limit? So the question is still valid. Okay, as h goes to 0, okay, to what value this expression tends to? Okay, I mean, we can still ask that question, right? But it's simply that we can't find it by plugging in h equal to 0. Okay, so what is that value that this expression tends to when h goes to 0? Is there any hope of finding it? Okay, so let me show you how to find it. Okay, and that's where the concept of limit becomes important. Okay, so you can only talk in terms of a value that the expression tends to. Okay, it never quite goes there. Okay, but we can sort of guess. What is the value that this expression, okay, is approaching toward. Okay, so how to find that? So this is how we can find it. It's actually a very simple, okay, method. Okay, it's just you expand the numerator. Okay, let's actually do that. Let's see what happens. Okay, you do x plus h squared minus x squared. Okay, how do you expand this? So you can find this by using a plus b whole squared formula, right? Remember this formula: a plus b squared whole squared is a squared plus 2 times ab plus b squared. You have to kind of remember that. Okay, you have to memorize this formula. Okay, I mean, you can prove it just by multiplying a plus b by a plus b. Okay, but it's kind of good so it comes in handy. You can remember in this formula. All right. So let's expand this using that formula. So we have x squared because x is a, right? B is like h, so I can write 2xh plus h squared, right? And then minus x squared. Okay? So in the numerator, so these two cancels out, and what you have is this, which you can write as h times 2x plus h. Right? That's what you have in the numerator of this expression. Okay? So what you have in the denominator, you have h, right? So your expression, if you just focus on this, this expression becomes h times 2x plus h divided by h, right? So these two h will cancel out. So you're just left with 2x plus h, right? And so, but you're trying to find the limit, right? Limit h goes to 0. So you simply plug in h equal to 0 here. So you just set this to 0 and you get 2x. Okay? So the limiting value of this expression is just 2x. Okay? So isn't this cool? Like you see, I mean, you couldn't evaluate it at first, right? Because the functional value didn't exist. But the limiting value still exists and it's just 2x. All right? So, so this is why the concept of limit is important. And this is how you find, okay, limits when, the functional value doesn't quite exist, okay? So let's just generalize this situation a little bit, okay? So let's say you have a general expression like this. Limit h goes to 0, f of x plus h minus f of x divided by h. Okay? Now you see this expression, okay, in this expression, the numerator is what? Numerator is 0, because if you set this to 0, you have f of x, and that is f of x, so the difference is just 0, and if you set h equal to 0, you have another 0, okay? So this is x, okay? So you have simply 0 over 0 type of form. So once again, the functional value, the value of this expression when h is 0 is undefined, right? But just as we saw here, okay, the limit may still exist. In fact, it does exist in most of the situations, okay? And we call that limit, just like here, okay, let's just compare these two. See, here, f of x is x squared, right? You can see that. And f of x plus h is simply x plus h squared, okay? So this expression, okay, so this is very similar to that, right? So this is a general expression of this, all right? And so I can tell you the name of this, but let's actually do a couple of more examples, okay? To kind of get a feel for this expression. So for example, let's take f of x is x cubed. All right? Can we find this? Okay? So then let's actually write this down. So we'll have limit h goes to 0. And then x plus h, f of x plus h is x plus h cubed. Do you see that? Like you simply replace x by x plus h, okay? And then f of x is just x cubed, and then you have h. Okay? So next what should you do? Okay? So just like in this problem, we're going to expand the numerator, okay? So how are you going to expand the numerator? What is the x plus h cubed? What is the formula for that? Okay, you don't need a formula, right? You know x plus h squared, so you can find it. You can just write this as x plus h squared times x plus h, right? And for this you can use this expression, and you can use foiling, like distribution and so on. Okay, collect the like terms, and you'll get an expression. And I'll write down the final expression. I'll not get into the detailed calculation, but this is the final expression. Okay, if you have done your calculations correctly, then you should get this one. Okay, x cubed. Okay, and there's a certain symmetry. Okay, so first you cube this. Okay, and then you write 3x squared h. You see, this 3 comes in here, and then you have the power of x decreases by 1, and you have an h, okay? There is no h term here, but an h appears, okay? So the next, the next expression is 3xh cubed, okay? So you see the power of x is still reducing, okay? As the power of h, this is h squared, and the power of h increases by 1, okay? So the power of x decreases, power of h increases, okay? So, and then the final last term is h cubed. Okay, it's just the cube of this term. Okay, so that's your x plus h cubed. Okay, so in this expression, you should write limit h goes to 0, and you have h in the denominator, Okay, and in the numerator you will have this whole thing, right? So let's write that down. X cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed. Okay, sorry, my handwriting is kind of getting worse, okay, as I'm going toward the bottom of the board, but I hope you can sort of understand it. So the important thing is that x cubed term cancels out, okay, and all of the rest of the terms has an h in it, okay. That's very important, okay. So you can write this. You can write this thing. I'll write it here, okay. So I'll just do it here. So this is equal to what? So in your numerator, I'll take one h outside the bracket. So you have 3x squared, right? And then here you have 3xh, and then you have h cubed. So that means you have to write h squared. You took one h outside the bracket, right? And you have an h in the denominator, right? So these two h cancels out, right? And you're taking the limit h going towards 0. So that means you have to set this h and this h to 0, okay? So both of these terms vanish, and you're left with simply 3x squared. Okay? So you can see that this limit, when f of x is x cubed, is 3x squared. Okay? So I'll do one final example, okay, of how to calculate this limit, and then we'll try to see if there's any pattern, okay, to to these expressions, like why you have 2x when f of x is x squared, okay, why you have 3x squared when f of x is x cubed, and so on. Is there a relationship between the function and its and this limit, okay? And we will also explain, okay, what this limit is called, because this limit is a very special limit, okay? It's used everywhere, okay, in physics, engineering, mathematics, okay, and so on, okay? So we'll get to that. Okay, so let's see another example, okay, of how to find this limit, okay, for another function. So let's say the function is x to the half this time, right? How do you find this limit? Does this limit exist? Okay, I mean, can we find this limit? That's always a question, right? I mean, so if we have, using tricks, if we have found the limit, then the limit exists. Okay, so let's try this function. Okay, and let's see what happens. All right. So you use this definition. Okay, when f of x is x to the half. So what do you get? So we are still trying to evaluate limit h going to 0. Okay. F of x plus h is what? X plus h to the half, right? And then minus f of x, which is minus this, right? And then you divide by h, right? Okay, so now what are you going to do? I mean, we can't expand this. It's half, right? I mean, it's not like a plus b whole square, right? So what are you going to do? Okay, so we have to use a trick here. Okay, what is the trick? The trick is we're going to write this expression as follows, okay? So we write this as it is, we just leave it as it is, x plus h to the half minus x to the half, okay? And then we multiply this by x plus h to the half plus x to the half, okay? And in the denominator, we have h, so we have to multiply that by this expression, x plus h to the half plus x to the half. All right. So do you see what we did? We multiplied the numerator and the denominator by the same number, same expression. Okay. And why did I choose this expression? Okay. See, the difference between these two is in the negative sign. It is in the sign, right? In this case, it's negative. In this case, it's positive. Okay. So we can use this formula: a minus b times a plus b. Okay, is a squared minus b squared. Okay, so the numerator, okay, if you think of this whole thing as a and this as b, so you have a minus b and this is a plus b, right? And we can use this formula. If you do that, then what do you get in the numerator? So I'll write it here, equal to, okay? In the numerator, you have the square of this whole thing, right, which is just x plus h. You see that? The square of it, x plus h to the half. If you square that, you get x plus h. And here you just have minus x, right? X to the half squared is just x, okay? And in the denominator, you have h times this whole thing, which is x plus h to the half, okay? Plus x to the half, okay? Now, what is the advantage? The advantage of doing it is x cancels out, so you have just h in the numerator, which will cancel out with the h in the denominator, okay? So you're simply left with this expression. So this whole thing is just what you have here, okay? So let me just, I don't know, maybe I'll just write it out here, okay? I'm sorry about that, but I don't have any space there. So this expression is equal to 1 divided by x plus h to the half plus x to the half, okay? And now I'll set h to 0, right? That's what you do in these problems, okay? If I set h to 0, I have 1 divided by, you have x to the half, and then another x to the half, so 1 divided by 2x to the half, okay? So now we are ready to make a general observation, okay? So we took 3 examples, and we found this limit, okay? And the limits are as follows, okay? So when f of x, okay, was x squared, the limit was 2x. When f of x was x cubed, the limit was 3x, right? This limit, this thing, okay? F of x plus h minus f of x divided by h going towards 0, okay? And when f of x was x to the half, what you got is this, okay? Which is half x to the minus half. You can write it this way, right? It should be clear shortly why I'm writing it this way, but this is the same as what you have here, right? It's a negative index, in relationship between negative and positive index, okay? All right. So so first of all, this expression is called the derivative of f, okay, at x, okay? So it's sometimes written as, this limit is written as df dx, okay? Which is called derivative of a function, okay? And this method is called differentiation, okay? This is derivative, this is called differentiation, okay? And so for these functions, these are the derivatives, so these are df dx, okay? And what is there a general rule here, okay? You see, when you have 2 here, then, the derivative has a 2 multiplying, the power comes here, okay? Here the power is 3, the derivative has a factor of 3, okay? Here you have a half shows up here, okay? So the general expression is, d dx, this is the d dx, this is how it's written, of x to the n, x to the power n. N can be anything, any number, okay? Integer or fraction or whatever, okay? This is equal to n x to the n minus 1, okay? You can check that this formula holds for all of them. When n is 2, okay, 2 minus 1 is just 1, so that's why you have an x, okay? When n is 3, then you have 3 minus 1, which is, this is actually squared, 3x squared. Okay, so you can check your, the previous work, and what we got is 3x squared, okay? And when, n is half, then you have, half times x to the power half minus 1, which is minus half, okay? So this is the general formula, okay, for the derivative of x to the power n, right? All right. So now we're going to see some properties of the differentiation or derivatives, okay? So for example, if you have 2 functions f and g, okay, you will have d dx of f of x plus g of x, okay, is equal to df dx plus dg dx, okay? How can we prove this, okay? So it's kind of like, distributive property, right? But we can prove this from, the definition, okay, of derivative. Remember that we wrote the derivative of a function, okay, is what? So if we call this as h, okay, a function which is the sum of these 2 functions, okay, then d dx of hx, oops, h is not going to work. I think we should use a different notation. So let's call it, I don't know, L maybe? Okay, let's call this function as L, okay? So d dx of Lx, okay, is going to be what? Limit h going to 0, okay, Lx plus h minus Lx, okay, divided by h, okay, right? So this is the definition of the derivative of the function L, okay? Now what we're going to do is we're going to simply write Lx as f plus g, okay? If you do that, what do you get? So limit h goes to 0 in the denominator a of h. Now, Lx plus h, what does that mean? It means fx plus h plus gx plus h, right? So let's write that down, fx plus h plus gx plus h, okay? And then minus Lx, right? So which is what? Which is just f plus g. So we can write this as fx plus gx. Okay? Now you see you can distribute this negative sign to these two terms, right? And if you do that, you can write this expression as h, and you can put these two side by side with proper sign, negative sign, okay? So you can write this as f of x plus h minus f of x, okay? And then plus g of x plus h minus g of x. You see that? Okay? So these two are, just written side by side, okay? All right, so now you can just distribute h to these, two expressions. And what you have, the first expression, this divided by h is just limit h goes to 0, is d of dx, df dx, right? And then plus, that expression is going to give you dg dx, okay? Okay, so we did not quite, say it explicitly, but I'm going to, say the following thing that I'm going to say now explicitly, but we used it here, which is that limit x going to c, okay, f of x plus g of x, okay, is equal to limit x going to c f of x plus limit x going to c g of x. Okay, so it's kind of intuitive, like, limit kind of gets distributed, okay? So that is something we used here. Okay, this is a property of limit, okay, which is true. Okay, and it's as you can sort of see, it's intuitive. Okay, I mean you can take the individual limits, okay, and add them up, okay, which is the same as adding the functions up first and then taking the limits. Okay? Anyway, it holds, it's true, and we used it here. Okay, all right. So let's get to the next law or rule, involving derivatives. Okay, so the first rule is this. Okay, ddx of f plus g is df dx plus dg dx. Okay, next. So next rule of derivatives or involving derivatives is the following: ddx of f of x times g of x is equal to f dg dx. Okay. F of x plus df dx gx. Okay, so this is called the product rule. Okay, so if you have two functions, okay, this is how it works. Okay, can we prove it? Okay, let's try to prove this. So let's call this thing, okay, once again as we have to give it a different name. So let's call it Lx, just like before. Okay, so what is the definition of the derivative? So dl dx, okay, is equal to limit h going to 0, Lx plus h, right, minus Lx, okay, divided by h, right? So what is Lx plus h? So you have limit h going to 0, you have h in the denominator, Lx plus h is just f x plus h, right, times gx plus h, and then you have Lx, which is just minus f of x, g of x. Okay. Now we are going to write the numerator, okay, in a slightly different form. This is how we are going to write the numerator as. Okay. So you have this. I'll just write the whole expression. The first term is f of x plus h times g of x plus h. Okay. And I'm going to subtract something like this: minus f of x plus h, okay, times gx. Okay. Did you see what I did? I left this x plus h as it is, but I changed g of x plus h to gx, okay? And then this term isn't here in the numerator, right? So you have to add this term. So you write plus f of x plus h times gx, okay, and then you write that one, okay, minus f of x times g of x, okay? And now what I'm going to do is that I'm going to just, sort of club the two terms together, like the first two and then the last two, okay? So if I do that, what do I get? So limit h goes to 0, you have h in the denominator. So in these two terms, you have a common factor, f of x plus h, okay? So let's take that outside the bracket. So inside the bracket, you will have g of x plus h minus g of x, right? And then you have these two, right? So what is the common factor between these two terms? It's gx, right? So let's write that down. You have g of x, and then inside the bracket, you have f of x plus h, and then minus f of x. Okay? So now once again, you can distribute, h to these two terms, okay? If you do that, see this, do you see this expression? Okay? This expression is just dg dx, okay? Right? And h goes to 0, so this is f of x, this is dg dx, this is gx, and if you divide this expression by h, you'll get df dx, okay? So what you have, so this expression is going to give you this following result, okay? I'm going to write it down there. Okay, maybe I should use a different color. Okay? So what you have there is, if you just distribute the limit, remember the limit can be distributed, right, to multiple terms, okay? And even through products, okay? Okay, so another property of limit that I should have said before is that limit x goes to c, if you have two functions, okay? Let's say f of x times g of x, okay? Then you should write this as limit x goes to c f of x. It's the product of the two limits, okay? Limit x goes to c g of x, okay? So this is a property of limit that holds, okay? So limit kind of gets distributed, okay? It's also very intuitive, right? You can sort of feel it that this should be the case, okay, for smooth functions particularly, okay. Anyway, so if you do that, if you just distribute the limits, okay, first divide the expression by h, okay, and then distribute the limits. If you do that and use the definition of the derivatives, then you get this: dl dx is equal to f times dg dx plus g times df dx, okay, which is what we set out to prove. Okay? This is called the product rule of the derivatives. Okay? And we proved it, you see, from the first principles, as I say, from the definition of derivative. Okay? Okay? So there is one more, one measure formula that you need to remember about derivatives. So let me write that down. Okay? Okay, so the last formula for regarding derivatives is this. It's called the quotient rule, okay? It's like d dx of f of x divided by g of x, okay, is g of x squared, okay? You square this thing, you take the derivative of the first function, or the function in the numerator, okay, times gx, okay, you multiply that by the denominator, minus the derivative of the denominator times the numerator. Okay, so this is called the quotient, rule of differentiation. Okay, so the previous one was the product rule. This is the quotient rule. Okay. All right. So we will, leave it there. And next time, we'll see one more rule. It's called chain rule. Okay, it's a very important rule in calculus, and we will be doing problems. Okay. So problems that use everything that we discussed in today's video. Okay, so I hope you learned something from this video, and thanks for watching.